Stony Brook. This is our 5th or 6th. It's a large number, so they happen often. Come again. Mini-school and geometry. And as a format, it will have 2 talks in the morning by our own Dror Varolin and Christian Snell. And then in the afternoon, Mihai Paun will give 2 talks also. The second of these talks will be a talk, which is also the first talk of Agnes conference, and it will happen in a different building. We'll tell you about that later. For any kind of reimbursement paperwork, please see Lynn and Lucille at the entrance, not right now, but during the coffee break. If you have any questions, ask us. And also make sure that you do ask the speakers questions, because the purpose of this is being a school, not a conference. So you should learn, and this means if you don't understand, you should ask and learn more by asking. And with that, we are very pleased to have Dror, who will talk about singular metrics for holomorphic line bundles.
Thanks, Sam. Yeah, it's a school I knew before, but to cover all this material, I couldn't really give a lot of details. There is a set of notes that I started to write, but I ran out of time. They're not edited yet. But I will give them to you if you email me, if you want to get any more details about stuff that's taught. Well, so it's a sequence of 4 talks that are somehow, the first 2 are sort of service talks, and then the last 2 are the details. And this is the kind of some of the analysis background that we need for the theorems that Mihai will tell us about in the afternoon. Let me get started. So I'm going to talk about, I'm going to separate my stuff into sort of 4 interconnected things. So the first one is a statement of Hormander's theorem, which I was tempted to prove, but I didn't believe I could fit everything else that I was asked to fit in here. It's not that hard to prove if you ignore the regularity part of the statement, as you'll see. Then after that, Hormander's theorem is a kind of vanishing theorem, classically, well, not classically, but geometrically first stated for smooth metrics. And we need to develop a theory of singular metrics, which are the key tool somehow in this whole business, or one of the key tools. And so to develop them in their notion of curvature, we'll need to talk about plurisubharmonic functions. Then it'll be easy to talk about singular Hermitian metrics. And I'll restate Hormander's theorem. And then at the end of the talk, I'll use it to kind of sketch a proof of an L2 extension theorem, which is also maybe the most fundamental thing needed in the rest of the lectures. The different thing about this L2 extension theorem is they've existed since about the late 80s, since about 1987. L2 extension theorems began to exist. Their usefulness increased, but in the last, I don't know, is it now, but 5 or 6 years, people have been trying to get optimal bounds for these L2 extension theorems. And so the idea was to present the optimal bound. But in all honesty, I cannot give you any true reason why the optimal bound is what it is in this short time. So I'm going to state what it is. I'm going to tell you some of the tools that are involved. And then it hopefully will inspire you to dig further. Okay, so let's start with Hormander's theorem. So it starts on a complete Kähler manifold with some holomorphic line bundle, L having a smooth Hermitian metric. And we'll assume that the curvature of this, so there's a little bit of notation here, but I'm going to have to some extent skip that. So a Hermitian metric gives you a norm on each fiber of a line bundle. And then line bundles are locally trivial, so you can try to measure the norm of a nowhere zero section in some neighborhood. And that will be some function, and the negative logarithm of that function you call phi. Because the curvature of this metric with respect to the turn connection attached to this data is dd bar of phi. So that's why the notation is there. Anyway, so we ask for this curvature to be positive, which means it's bounded below by some Kähler form omega, which we fix. And then the theorem says that if you've got any L-valued N1 form, alpha, which is D bar closed and has a finite L2 norm with respect to this lower bound Kähler form, then you can find an N form with values in L, solving the equation D bar U equals alpha, and with this L2 estimate. Okay, so, and then there's one additional piece of information which is important, which is that if this form alpha was a smooth form to begin with, so here we're just working in L2 spaces, but if it were smooth, then this U would also be smooth. We're going to need that property. Okay, so just a couple of remarks. It's a kind of, for the algebraic geometry-minded people in the crowd, which is probably the majority, this Hormander theorem is a vanishing theorem. It says that every closed form is exact, but it also provides estimates, and those estimates are what give you a lot of advantages in various constructions. As for the smoothness of U, this has nothing to do with the L2 estimates directly. It's a regularity theorem for D bar. So it's true on a number of levels. There's a number of simple ways to prove this, sometimes called Weil's lemma. Okay. That regularity part will be important later when we go to singular metrics. Okay, so maybe let me just go back for 1 second. So we're going to want to generalize this to a situation where the finiteness of the L2 norm of U forces U to vanish somewhere. One of the ways to do that is to take the function phi to be a singular function, something like log norm z to a large power. Then if you have finiteness of the L2 norm, U would have to vanish at the origin. So that's sort of the trick to constructing solutions of the D-bar equation with vanishing. Okay. So to make these singular things that still have some positive curvature in some sense, we're going to introduce plurisubharmonic functions. So these are plurisubharmonic functions are functions that are subharmonic along every complex direction. So first you start by looking at subharmonic functions, then you go to plurisubharmonic functions. And so I said this. To generalize the theorem to singular metrics, we need to understand the local properties of these singular metrics. Now, when you take a complex analysis course the first time, you may or may not see subharmonic functions. They're often introduced as continuous functions because it's enough to solve the Dirichlet problem. But here we really want to focus on singularities. So we have a little bit more general approach. It's also classical, but here's the definition. So you take a domain in C, and you take an upper semi-continuous function. So it means that the lim sup as x goes to y of u of x is less than or equal to u of y. Jump up. So this function will be subharmonic if it's not identically minus infinity in any component. This is a convention. You could include those, but then you have to change the statements of other theorems. But the most important one is if you take any compact subset of your domain, and then you take a continuous function on the compact subset, which happens to be harmonic in the interior, then if your function is less than or equal to the harmonic function on the boundary, then it stays smaller than the harmonic function in the interior. So that's why it's subharmonic. So the notation is used in SH of omega. So it's not hard to deduce from this that these subharmonic functions form a positive cone. Also, if you have any family of subharmonic functions, then you can look at the supremum defined pointwise of these things, and that could be infinite, and it might not be upper semi-continuous. But if it's finite, then you can form its upper semi-continuous envelope, and that will be subharmonic. So the sup and the subharmonic interact well together. You'll see why a little more clearly in a second. And then maybe a better way to take limits of subharmonic functions is when they're decreasing. Because if you have a limit of decreasing functions, which is not identically minus infinity, it's automatically going to be upper semi-continuous, and then you can check that this definition is satisfied by that limit. So this is kind of gives you a topology on the set of subharmonic functions, which is useful. But maybe the most important characterization is that the subharmonic functions satisfy the submean value property. So a function subharmonic if and only if, at any point, if you fit a disk into the domain centered at that point and compute the average value of the function on the boundary of the disk, then that's bigger than the value at the center. So for upper semi-continuous functions, you can define the integral, so that's good. So from that submean value property, you can now deduce a lot more about subharmonic functions. For example, from the definition, this isn't easy to see, but the sum of two subharmonic functions is subharmonic. The log modulus of a holomorphic function is subharmonic. And notice that if f has zeros, then you get something not smooth. Otherwise, it's harmonic. If you have a convex increasing function, then you can compose your subharmonic function with this convex increasing function from the left, and you again get a subharmonic function. This allows you to design subharmonic functions that grow very, very rapidly. It's a very useful tool. Many other things as well. The other thing that's not quite a consequence of the mean value properties I stated, but it's a consequence of the proof of that theorem, is that subharmonicity is a local property. So if you have an upper semi-continuous function, you want to check if it's subharmonic, you just have to know that every point has a neighborhood where it's subharmonic. And this is the thing that allows you to generalize this notion to complex manifolds as well. Okay, so maybe, right, another thing that follows from the submean value property is that the subharmonic function is automatically locally integrable. And so this is proved using the area version of the mean value property. So if the central value dominates the value on the average on the circle, then you can also integrate over the set of circles. So you get an area mean value property. And then you can kind of see how it's linked to local integrability. Anyway, I'm not going to prove it, but it's not that hard to prove, but you can sort of guess on the fact that there's an integral involved over an area. So maybe for us, the thing that's going to allow us to define the curvature properly is that the subharmonic functions are characterized by the following theorem. So if you have a locally integrable function, then it's going to be subharmonic if and only if it's upper semi-continuous. Of course, it's only locally integrable. It's not defined everywhere, but there's a way to modify it, to make it upper semi-continuous. And if you compute its Laplacian, then that's a positive function. So this Laplacian in the sense of distributions is what's computed here. So I gave you the definition here, but in higher dimensions I won't bother doing that again. Anyway, there's a way of defining an object, which is a bit weird, but we understand well, and the positivity of that object is equivalent to subharmonic function, to being a subharmonic function. Okay, now let's go to plurisubharmonic. I already said that a function is plurisubharmonic if it's subharmonic along every complex direction. So I chose lines, but you can take any complex curves. The notation is PSH of omega. And so the first example we get is the log square modulus of a holomorphic function is plurisubharmonic because holomorphic functions are functions that are holomorphic in each variable separately. Okay. If you take the mean value property on circles, on lines, and then you integrate over the set of lines using Fubini's theorem, then you get this control of a plurisubharmonic function by the average value of the integral on the sphere. Right, and then of course you can integrate over the radii like before and get a volume bound. Now, these functions are not, this is not a characterization of plurisubharmonic functions. These functions, functions which satisfy this are actually called subharmonic functions, even in higher dimensions. They don't have the as nice properties as plurisubharmonic functions, but still you can use them to deduce the same thing, that you have a locally integrable function. I guess maybe I didn't emphasize this point enough, but the fact, I started out by saying that one thing you can deduce about a subharmonic function is it's locally integrable. But to form this distributional Laplacian of a function, you need the local integrability. It's part of what you need in the data for the definition. Okay. Anyway, just like before, in the subharmonic case, we get a bunch of corollaries, this cone property, we get that the supremum, finite suprema of families of plurisubharmonic functions have plurisubharmonic upper semi-continuous envelopes. Decreasing sequences, which are not identically minus infinity, are plurisubharmonic. And then the convexity thing, you change a little bit. You take functions which are convex in each variable separately. And if you do that, and then you stick a plurisubharmonic function in each of the variables of this kind of pluriconvex function, then you get something plurisubharmonic. So for example, the sum, the maximum, and then the log of the sum of the exponentials. Those are all examples of convex functions. So you get plurisubharmonic functions. So for example, the log of the sum of squares of holomorphic functions now is plurisubharmonic. And that's actually an interesting example because the theorem that we are going to prove at the end of the lecture, you can use it to show that the log of sum of squares of plurisubharmonic functions multiplied by a constant, property 1, are dense in the set of plurisubharmonic functions in the L1 log and pointwise sense. That's a kind of regularization theorem of de Mailly that's very useful. Okay. Anyway, then we also get this theorem that if you have a distribution, then it's plurisubharmonic, meaning it's given by integration against a plurisubharmonic function, if and only if dd bar of this distribution is a positive 1-1 current.
Against the test function?
Sorry?
Given by integration against the test function, I'm not sure.
No. I mean that
What you mean there?
so it's a distribution. So I guess a distribution acts on test functions. And so what I mean is that this distribution is given by integration against a test function. Well, you take a plurisubharmonic function times a test function. That's the distribution. And that's true if and only if dd bar of u is a positive 1-1 current. Okay, so now we've got our plurisubharmonic functions. The next thing, so this multiplier ideals don't totally fit into my lecture that much, but I think it's something that may be needed later, so I'm going to discuss them. But plurisubharmonic functions are definitely needed to get interesting properties of these multiplier ideal sheaves. And so, okay, so given a measurable function, phi on some open set in Cn, you can look at the set of germs of holomorphic functions at P, so that if you take f squared and multiply by e to the minus phi, that's still a measurable function, then you want this to actually be locally integrable in some neighborhood of P. You don't just any neighborhood where the germ is defined. So this actually forms an ideal if you have a function which satisfies this and you multiply it by any holomorphic function, it's still going to be integrable. So that's called the multiplier ideal. It actually comes from the theory of partial differential equations originally. You tried to prove some estimates in the theory of partial differential equations and you can't And so then you multiply something by some functions and force the estimates to hold. And that defines an ideal. So the modification of this was introduced by Nadel. This is a definition given by Nadel. And he actually did use it for the Monge-Ampère equation in a very similar way. But anyway, they turn out to be fundamental in complex and algebraic geometry. Anyway, they form a sheaf, which is called the multiplier ideal sheaf. And then I just make this observation that if you add some function which is bounded locally, you don't modify the multiplier, you don't modify the integrability property. So for example, a smooth function, you don't modify the integrability. Okay. Anyway, if you take the theory at this level of generality, these multiplier ideal sheets don't have any nice properties. But if the function, called the weight function, is plurisubharmonic, then the ideal does have nice properties. And maybe the first theorem that you prove is that if you have a plurisubharmonic function, this ideal sheaf is coherent. So that's called the Nadel coherence theorem. And so for coherent sheaves, there are lots of results. This coherence makes something like the Kawamoto-Five vanishing theorem work. And I'll get to that one a little later. Okay. So maybe I'll just do some examples to compute these multiplier ideals in some simple cases. They're not easy to compute in general. But anyway, I'm not going to compute them exactly. I'm just going to show when they're trivial, when they contain the function 1 or not in my examples here. To some, well, maybe a little more, but anyway. Right, so suppose you take some germ of a holomorphic function which vanishes at the origin, but the differential is not identically 0 on its domain of definition. And then you consider the analytic hypersurface Z, which is the set where f is 0. So now we're going to take our weight function to be s times the logarithm of the square norm of this f, where s is some positive constant. So if you go to a point where the differential is non-zero, then this function f can serve as a local coordinate, which for psychological reasons I renamed t, in some neighborhood of p. And then you can try to compute the integral over a neighborhood of p of e to the minus phi s times the Begg measure. So this is to check whether 1 is in the ideal. And so when you do that, you have the coordinate t and some n minus 1 other coordinates. The other coordinates will give you something finite. The only trouble could come from this t. And the integral is more or less this one. Anyway, its finiteness is the same as the finiteness of the other integral. And then that's an easy calculation to see that it's finite if and only if s is less than 1. However, if you're at a point of singularity for this z, so a point where df vanishes, then the situation can be different. For example, if you take a function whose zero set is a horizontal line and then a parabola, and they meet at the origin, so that's a kind of singularity. You want to try to compute that integral, but it's difficult to compute actually. And so what you do is you do a change of variables. Now, this change of variables is biholomorphic away from the set where u equals 0. In fact, its Jacobian is holomorphic Jacobian is u squared. So since integrals don't see sets of measure 0, you can make this change of variables. This map is a composition of two blowups. And then when you check this change of variables, you get an integral which is a product of linear terms to powers, a product of linear terms. And then you can check whether or not this is finite. And you'll find that it's finite if and only if S is less than 3/4. So it drops down. A more favorite example is to look at a cusp, but then I'd have to do 3 blow-ups. It just looks more confusing. And I think the number is 5, 6 or something like that for a cusp. Okay, so this is when you have singularities along a hypersurface. You could also have isolated singularities. So for example, you could take in Cn the log of the square modulus of the coordinates z1 through zn. You could try to compute this. So in this case, this finiteness, this actually, I guess, computes the multiplier ideal in this example. If you want to see if a function is square integrable, you've expanded in a Taylor series, or a homogeneous expansion. And then when you write down this integral and you use orthogonality appropriately, you get this identity. And so now you can see, well, you can check whether or not that's integrable. You look at the lowest order term, and then just make sure that the power is bigger than -1. So, of course, you might be at a point which is not the origin, then the multiplier ideal is trivial. And then if this constant c is small enough, it'll also be trivial. But otherwise, the multiplier ideal will be some multiple of the maximal ideal, some power of the maximal ideal. Okay. So you can go a little further from that last example by defining the notion of Lalong numbers. It turns out that plurisubharmonic functions are sort of regular. Part of it was that you get this current, which turns out to be a positive, so positive 1-1 form with measure coefficients. That's a kind of regularity. And so it makes the functions behave sort of nicely. In particular, this limit, if you look at phi of z and divide it by log mod z minus x, this limit will exist. Right, so that limit is called the Lalong number. And from the way I've defined it, it's not even obvious that it's independent of the coordinate system, but it is. In fact, it's a theorem of Su that for a plurisubharmonic function, the Lalong number is independent of the coordinate system. More importantly, you could look at the subsets of omega where the Lalong number is bigger than some constant c. And so if you just look at a fixed Lalong number, that could be a messy set. It's not so bad. But this tells you that if you look at where all the Lalong numbers are bigger than some level, you get closed analytic sets. They could be quite bad. There could be countably many components and things like that. But anyway, it's still very useful. So using these Lalong numbers, you can say something about when multiplier ideals are non-trivial. So I wasn't sure if somebody wanted to use this or not. So this is a useful lemma, so I thought I would present it. It's called Skoda's lemma. So it says that if the Lalong number at a point x is less than 1, then the multiplier ideal is trivial. If the Lalong number is bigger than the dimension, so bigger than or equal to the dimension, then the multiplier ideal is going to be non-trivial. And how deep it sits inside the power of the maximal ideal depends on how large the Lalong number is in this kind of linear way. Affine linear way. So, and then so from those two properties, it's sort of obvious that the set of points where the multiplier ideal is non-trivial sits between this E1 and E dimension of phi. It's just a set where the Lalong numbers are bigger than or equal to 1. So if they're less than 1, then it's integrable. So you're going to have no zeros there. Okay, so Anyway, so those statements 1 and 2 are not trivial to prove, but they use some properties of plurisubharmonic functions which I didn't really have time to define. So, for example, these submean values, they not only dominate the function, but they're increasing functions. And they're actually not just increasing function of the radius, they're increasing function of the logarithm of the radius. So it's things like that that come into this proof. And all those things are consequences of Green's theorem or Stokes' theorem or some version of Stokes' theorem. The positivity of the Laplacian comes up in the divergence theorem. Okay, so let me move on to singular Hermitian metrics. So, given a smooth Hermitian metric on a holomorphic line bundle, we already discussed how to compute its curvature. If you have this metric H and you choose a holomorphic frame, then you can compute the square norm of this frame with respect to H. And then you can compute the negative logarithm of that positive function. And that's the function phi we've been talking about before. And of course, these are smooth functions in this case. And then the curvature is exactly dd bar of this negative logarithm. And so its positivity means that you want this 1-1 form to be positive. So, well, excuse me. Its positivity means that that function, negative log h of c should be plurisubharmonic. Except it's smooth in this case. Anyway, there's maybe a remark is that this, even though the function itself depends on c, dd bar does not. That's probably a calculation you've all done. Right, so subharmonicity plus smoothness is what you're asking for here. But we know how to define plurisubharmonicity without smoothness. And so that leads to a generalization of the notion of singular Hermitian metric. Right, so I just said this. So suppose you're given a holomorphic line bundle. Then you want to check whether or not a metric is a singular Hermitian metric. Well, first of all, any metric can be seen as a section of this dual bundle tensor with its complex conjugate. If you act on a pair of vectors in the line bundle over a single point. And so you can just take this to be a measurable section, which is a well-defined thing. And then if you use a holomorphic frame, you can require this function to be, well, actually, this part is not dependent on the holomorphic frame. If you take any smooth frame, you can require negative log of h of the frame to be locally integrable. So then you say that the metric h is a singular Hermitian metric. It's not just a measurable function, but the negative logarithm of the local, well, the local potentials are locally integrable. So you can define, in particular, their curvature current in the sense of distributions. And this is called the curvature current of a singular Hermitian metric. And then those are still too general to deal with. So most of the time, so not all, there's one paper by Haken, Demai, Haken, and Paun about some L2 extension problem related to the abundance conjecture where they don't assume this quasi-positivity. So you can deal with it as long as it's under some control. But in most cases, what you want is for this curvature current to be almost positive. So it's positive, except maybe it has some negative things, but you can control those with some smooth form. And then you actually say that it has positive curvature if these local functions are plurisubharmonic. Curvature current is not negative. So that's a singular Hermitian metric for a line bundle. Now, for a vector bundle, you run into real problems trying to generalize this. Because to compute the curvature, well, it's not just a matter of taking some function. You can't just take a logarithm and take dd bar, even though it formally looks like that. You have to multiply the differential of the matrix in some frame by the inverse of the matrix. And if that thing is, that's perfectly fine for the differential to be defined and for the inverse to be defined in the sense of distributions. Well, the inverse is already a problem. But anyway, the product of those two is the real problem. You can't multiply distributions. They don't behave well when you multiply them. So that's why, until recently, we've been sticking to line bundles for these things. So you end up defining singular Hermitian metrics for some vector bundles, automatically including some positivity of the curvature in there. But not, you don't define their curvature. You just say what it means to be positively curved. In fact, you sort of can't define their curvature in general. There will be a lot more about that later, but this is how this relates to one of the subjects of the talks. Okay, so here's an example. Suppose you have a holomorphic line bundle and a bunch of meromorphic sections of this line bundle. So if you take a holomorphic frame, then you can find meromorphic functions on the neighborhood where the frame is defined, so that this meromorphic section is just a meromorphic function times this frame map. That's just the definition of being meromorphic. And then you can define a metric H by taking 1 over the sum of squares of these meromorphic functions times the dual frame tensor with its conjugate. Now if you were to change holomorphic frames, the f's would also change, but in such a way that this expression for H would not change. So anyway, the thing is that if you take the negative logarithm of this H of C, it's just the log of the sum of squares of the f's, and that's always locally integrable. So the notation sometimes for this is 1 over the sum of squares of the sections for this metric H. And I should say that this is in general not quasi-positive. If you write locally, if U is a Stein neighborhood, for example, then you can write the Fi's as Gi's over Hi's, clear denominators, and then you'll see that this sum here becomes sum of squares of holomorphic functions minus some other sum of squares of holomorphic functions, and then minus logarithm of this, well, maybe sum of squares of holomorphic, log of sum of squares of holomorphic functions minus log of absolute value squared of one holomorphic function. And that minus gives you, when you take dd bar of that, it's 2 pi times the current of integration over the 0 set of that function. And a minus sign on that, you can never bound that below by a smooth form. So for these things to be quasi-positives, these sections always have to be holomorphic. And then they're automatically positive. Okay. So anyway, Hormander's theorem extends to the setting of singular Hermitian metrics, but not as I wrote it before. The way that I wrote it, I said you start with a complete Kähler manifold, and that is, well, it's tricky to work with. So, of course, the theorem is true for smooth metrics, and the way that you prove the theorem uses the smooth theorem. You need to regularize the metrics. And so just to make things as easy as possible, I asked for the manifold to be Stein. I said Stein-Kähler because of a first version of this theorem that I had written, but I'm not using the Kähler metric. And every Stein manifold is Kähler, so it's a little redundant. But anyway, it's the same theorem as before, except that the underlying space is Stein. And now, well, there's one added piece of information that you get, which is that if you look at the restriction of U to the 0 variety of the multiplier ideal sheaf of the singular Hermitian metric, then it must vanish. And the reason is that this U is smooth. And so if its integral is finite, and you have non-integrability of e to the minus phi, U must compensate for that by vanishing to a large enough degree. So if you concoct singular Hermitian metrics with high singularity, you can not only make U vanish, but you can force it to vanish to high order. So then the whole game becomes constructing these metrics, and they, being plurisubharmonic, or quasi-plurisubharmonic, are constrained by the global geometry of the space. And so there's a back and forth between the geometry of the space and these singular Hermitian metrics. Anyway, as I said, the proof involves a kind of regularization process, which would be very difficult to get into the details here. So I skip over it by requiring Stein manifolds. Okay. So one corollary of this is this kind of vanishing theorem like we had before is now a little bit improved, a lot improved. If you have a compact or weakly pseudoconvex scalar manifold and a holomorphic line bundle with singular Hermitian metric of strictly positive curvature, then you have vanishing of the first cohomology, this vanishing here. So this comes almost directly from Hormander's theorem. For Hormander, to apply Hormander's theorem as I've stated it, you have to work with certain manifolds. For example, for projective manifolds it will work. But to get to this category, you have to do something a little different. But actually, even more, the higher cohomologies also vanish. And this uses Hormander's theorem as I've stated it, but it goes through a kind of sheaf argument analogous to the proof of the abstract de Rham theorem. And so the notes of Demailly have a very nice complete proof of this if you're interested in how to prove this vanishing theorem. Okay, so now, good. Let me come to the last part, which is the L2 extension theorem. So first of all, there's a very general L2 extension theorem I'm not going to state here. I think the one that we need for these lectures is just concerning certain kinds of manifolds. So they're going to be projective families. So a holomorphic family is a complex manifold with a proper holomorphic submersion to the disk. And then you say that the family is Kähler if the total space of this family is a Kähler manifold. And it's projective if you can find a line bundle with a smooth metric of positive curvature. So here's the L2 extension theorem for projective families. I guess it works for Kähler families as well, as long as the manifold, well, it's probably true by now for all Kähler families, but anyway, projective is safe. See? Okay. I'll get to why that is later. So if you have a projective family whose fibers are n-dimensional, and you have a holomorphic line bundle over the total space with a singular Hermitian metric, which is not identically infinity when you restrict it to the central fiber, and then it has non-negative curvature in the sense of currents. Then, given any holomorphic n-form with values in L, whose L2 norm is finite with respect to this singular Hermitian metric, you can find a holomorphic n+1 form with values in L over the whole family, whose restriction to the central fiber agrees with S wedge d pi, so pi is the map to the unit disk. Since it's a submersion, d pi is never 0. So you can write any n+1 form as an n-form wedge d pi. And so I'm saying that when the n+1 form is S, its restriction to the fiber is little s wedge d pi. And then you also get this L2 estimate, and the constant pi is the innovation of the last several years, 6 or 7 years. So I've been teaching this theorem in my several complex variables class, and I think this is, if you haven't seen this theorem before, it's a very hard theorem to absorb the first time you see it. Hopefully you'll see it so many times today that by the end of the day you'll absorb it. Okay, so this version of the theorem was proved by Su in the mid-90s. I guess this version was actually just stated in his 2001 paper on the deformation invariance of plurigenera. But his estimate, he didn't need the Sharp constant, and so he didn't know the Sharp constant. In fact, he asked me if I knew how to get the Sharp constant back then, and I didn't. But anyway, so his constant was larger, but I said that this constant is sharp, but it's actually not difficult to see that it's sharp. If you just kind of shrink your family down until it becomes infinitesimal over the origin, then sort of any section automatically extends to a neighborhood. And then the L2 norm, if you take the appropriate limits, you'll see that the constant has to be pi for this really, really tiny family. So pi is the sharp constant. And in the coming lectures, this sharp constant version is absolutely crucial. So it's that interaction when you take this limit and see what the sharp constant should be. And if you actually get it, it means that families are kind of well behaved when they're larger. The worst ones are the ones that almost don't vary at all. Okay, so anyway, the first person that got this sharp constant was Zbigniew. He was interested in a long-standing conjecture called the Swita conjecture, which is about the curvature of a certain metric you get on Riemann surfaces, defined by Swita in the 70s. So he followed a kind of recipe of Osawa, and then found a very ingenious way to reduce the constants. And that's what I'm going to explain to you in a little bit. Anyway, there were generalizations after that by Guan and Zhu. So Klodsky's proof was a little more economical, but made it much harder to read. So Guan and Zhu didn't care about this economy. They wanted to make it more similar to previous proofs, but not at the cost of making it easier to read. And so it's still at least as hard to read. But anyway, the two proofs are morally very, very similar. But there's an entirely new proof that came out on the archives about 3 years ago and was finally published last year, late last year. By Berenson, or maybe even this year, by Berenson and Lemper. That's my favorite proof, and that's the proof I would have liked to give here, but I'm in the service of a larger cause. So their proof does not involve direct use of the D-bar theorem. So essentially, their proof goes like this: you have your submanifold from which you want to do the extension. And then the submanifold is cut out by a holomorphic function, or should be the polar set of appropriate Plurry subharmonic functions. Then you can deform the ambient manifold and shrink it down onto the space. And then this deformation, for each value of the parameter of the deformation, you're going to get some constant. And what you prove about that constant is that it's decreasing. The decreasing property is a kind of convexity that comes from the Plurry subharmonicity. And so Hormander's theorem gets into there. But it turns out that this is Mihai is going to explain the tool, I'm sure. Or maybe Christian even. No, neither one? Okay. Anyway, at least it'll probably get brought up. But anyway. So this kind of increasing property is a fact of something. So it's bounded and convex. And if you define that correctly, that forces it to increase. So everything looks very, very natural. And the convexity comes from the Hormander estimate. So convexity is a kind of curvature. You compute a curvature of some bundle that appears in this problem. And that curvature being positive is a consequence of Hormander's estimate. So you bury Hormander's theorem somewhere very far away, but very, very general. I think it should be used for many, many things. But anyway, so it's a much nicer and more intuitive proof if you accept this curvature positivity. Okay, so the proof of extension follows a kind of standard strategy. What you do is you take a section you want to extend. You first extend it holomorphically in a bad way, and then you cut it off to make a good, smooth extension. And then you correct it with Hormander's theorem to make it holomorphic. And the estimates from Hormander's theorem give you the constant. Anyway, to get the good smooth extension, we get to the point of why I took a projective family in this case. So the point of a projective family is I can actually find a hypersurface in it whose complement is a Stein manifold. So the way you do that is you take your ample line bundle, and if you take a sufficiently large power, it's going to have a section. Cheating a little bit, you may have to shrink the family a little to get a finite power to give you a section. But anyway, we'll be taking some limits that make it clear you can do that. And then if you take the negative log square norm of that section, that gives you a plurisubharmonic exhaustion of x minus the zero set of the section. And that's a theorem of Grauer, that's equivalent to being Stein. So anyway, we reduced to working on a Stein manifold, and then there's this kind of abstract nonsense that tells you that you can extend any holomorphic section from any subvariety to a global holomorphic section. So that can also be proved using Hormander's theorem, but it's a vanishing theorem. But you don't need estimates for that. Anyway, of course you get an extension, but it has no L2 estimates. So to get L2 estimates, you take a relatively compact domain, and then you do get a finite norm. Unfortunately, it'll blow up as you increase the domain to exhaust the whole Stein manifold. And so this is where you tame that extension by multiplying by some cutoff function whose form I'm going to take to be a smooth function on the positive real line, values between 0 and 1, of log 1 over the square modulus of the holomorphic submersion. Anyway, so as I said, it's a positive function less than or equal to 1. It's going to be identically 1 on some neighborhood of infinity, this particular neighborhood. And then it's going to be 0 on a neighborhood of the origin. And then, so it's kind of 0 on a tiny neighborhood of the origin. I'll draw this quickly. Zero on this, say, 2 epsilon, something like epsilon here. And then a log of 1 over epsilon, which is a huge number, it creeps up slowly to reach 1, and then it stays 1. And so its derivative is more or less the slope of this line. So that's why you have those bounds. Should have probably said epsilon over 2, not 2 epsilon. Anyway, it doesn't matter. So, but note that because this function chi epsilon is identically 1 on a neighborhood of infinity, this composition is going to be 0 on a neighborhood of the central fiber. It's going to be 1 on the neighborhood of the central fiber. So the thing is holomorphic. So when you compute d bar, it actually vanishes on a neighborhood of the central fiber. And then you want to find a section U with good L2 estimate, which solves the equation d bar U equals this alpha. And U restricted to the central fiber is 0. Because then S tilde minus U will be an extension. Anyway, so to do that, we're going to use Hormander's theorem, but maybe cleverly manipulate it. So let me show you how I use Hormander's theorem here. So suppose you're given some smooth n+1 form alpha, and you're looking for a section which has the finite L2 norm. You assume that such a section exists. But let me take it with respect to not the weight e to the minus phi, but the weight e to the L minus phi for some smooth real value to L. Now, if there is a solution, then there's one of minimal norm. So minimality means that it's actually orthogonal to the space of holomorphic functions. Any two solutions differ by a holomorphic section. And so the minimal solution must be orthogonal to the holomorphic sections in this L2 norm. Okay, and so, right. So on the other hand, if you now take this function u0, multiply it by e to the L, then by just trivially becomes orthogonal to the holomorphic sections in a different way, L2 of e to the minus phi. So therefore, it is the minimal solution of this equation. So it's d bar, v is the minimal solution of the equation d bar v equals d bar v. Okay, and so when you write down what that is, you get this other form, beta. And now you have this solution of minimal norm. So any estimate you get on any solution is going to be an estimate on the solution of minimal norm. And Hormander's theorem gives you an estimate for some solution, which you don't know to be the minimal, but it automatically estimates the minimal norm. And so you get, for this v, you get this estimate. So now you rewrite this in terms of this u0. So, as I said there, you have this equality trivially, and then Hormander's theorem tells you this estimate. Now you plug in the beta, and now you expand. Then you use this inequality on the last term, that twice the real part of AB is, you take A, replace it by A times the square root of capital A, and B by B divided by the square root of capital A, and you apply the inequality for A equals 1, you'll get this one. And then you collect the terms, and that's the estimate that you get. Okay, so if we return to our form alpha, what we want to do is choose functions A, L, and phi, metric phi, so that this norm is finite and has a good bound. So in fact, what we really want is for this u to vanish along the zero variety. But notice that alpha is actually 0 on a neighborhood of the central fiber. And so you can choose weights that are very, very singular there. But there are other things you have to account for. Anyway, so that's a game, and this is the part where it becomes less intuitive. It just looks like through experience of calculating, you know how to choose the correct functions. And so anyway, with the right choices, you get this vanishing. And then for each choice of epsilon, you'll get an extension which satisfies on the domain omega the estimate with the constant pi plus something small that goes to 0. So I haven't told you how because I haven't written down the functions. And it wouldn't help you if I just wrote them down. It's a long calculation to show as well. But you can dig into the paper at this point if you want. Anyway, once you have this estimate, then if you have control over the L2 norm, let me go back. If you have control over this L2 norm, then locally you have control over the pointwise norm by the submean value property. So that means that having a uniform bound on this compact set omega, you can use Montel's theorem. You have a bounded set of holomorphic functions on each neighborhood. And Montel's theorem and some diagonal argument will let you pass to a convergent subsequence. And so then you'll get a section S omega, there shouldn't be a tilde there, satisfying this estimate on omega. And now you can play the same game by increasing omega. You can also then increase the family that I needed to shrink down to get my hypersurface. So anyway, once you have this tool, you can keep using Montel's theorem. But now, so now you've got an extension of your section, but away from this horrible subvariety you had to remove to get a Stein manifold. However, you have L2 estimates. And so you can go, say, to a smooth point of this variety, and expand the section in the Laurent series along the defining function near the smooth point, and then check what the L2 norm does, and you'll see that there are no poles possible if you have a finite L2 norm. It's the calculation we did for the multiplier ideal way back in the example. And so that means that this thing actually doesn't have any poles, so you can extend it across the smooth locus, and the singular locus has higher codimension, so by Hartogs you can extend across that as well, and you get an extension to the whole family.
Questions?
So I already asked you this question some time ago.
Sure.
So you mentioned that in order to get these optimal constants, there is a certain choice of certain functions there which is involved.
Yes.
I mean, is this clear from the proof that this constant cannot be improved? If you choose even more cleverly, the function should be the case. But
It is possible to improve it but not in a universal manner. So, I mean, you have to define the universe in which you're working. So what I'm saying is that as soon as you shrink down to this really tiny family, you can't get a better constant than this constant. And so, on the other hand, maybe you never work in the situation where that happens. Like if you're working in some non-moduli space where you stay away from the boundary, you probably could improve the constant. That would be my guess.
So you said that it's hard to extend the concept of curvature from line bound to higher dimensional, right?
It's not only hard, it's impossible. There are papers about how the curvature is not defined.
But why do you want to do it?
Why do you want the curvature?
Yeah.
Okay, that's a good question. So, well, the curvature appears in Hormander's theorem. This is the thing I was thinking about proving exactly for this question. So what happens is, if you have your d-bar operator, you can form the Laplace Beltrami. So, thanks. So the point is that, so this is acting on some Q form with values in a holomorphic vector bundle. There's two ways to see a Q form with values in a holomorphic vector bundle. One as a Q form, the other as a section of the bundle lambda Q. As a section of the bundle, it's actually a zero form, but not of a holomorphic vector bundle. It's a non-holomorphic because of the Q. And so, but it has a d-bar Laplacian, a natural one associated to it from this data. And so there you just, so because it's a zero form, nabla bar would be zero, so the Laplacian would be this. And the Bachner formula, Bachner-Kodaira identity, is that the difference of these two is the curvature. And so if you have positive curvature, you have a lower bound. This is always a positive term. If you have positive curvature, you have a lower bound on the Laplacian. If you can solve the Laplace equation for a d-bar closed form, then your automatic solution is also going to be d-bar closed. In fact, it's going to be d-bar star of something. And that solution will satisfy the estimate automatically. So anyway, the answer is that the curvature gives you a lower bound for the eigenvalues of the Laplacian. And that's what you want in order to solve d-bar.
So instead, it's some like kind of positivity of the curvature.
It's useful. Sort of, yeah, I mean, that's true. Although sometimes you can have something smooth positive around. And then the place where you can insert the singularity can't be positive. So you want to have a notion of making it, not very negative. So that's sort of the reason. Sure.
Any further questions? Okay, let's thank you all again.